If I have two vectors in three-dimensional space, u being u1, u2, u3, and v being v1, v2, v3 in component form, I'm going to define the dot product of the two vectors to be this. I need to make sure that I use the little dot and not the cross symbol, the times symbol, because later that's going to mean something else to us. The dot product of two vectors is a number. The good news is this is very easy to calculate. The bad news is we have no idea why you should concern yourself with something like this. Not yet, anyway. Calculating something like this is perfectly straightforward. We still have to figure out whether or not this has any meaning to us or not. One thing I can immediately see is that if I dot a vector with itself, the number is the same thing that I get when I calculate the magnitude of the vector, except I haven't done the square root. U dot u is the square of the magnitude of vector u. The dot product, therefore, has something to do with lengths of vectors, but there's more to it than that. We know previously that a vector is the length of the vector multiplied by the cosine sine vector that goes with u in this case. V is the length of v multiplied by the cosine sine vector that goes with v. I'll call the angle that u makes with the positive x-axis alpha, and the angle that v makes beta. Therefore, the angle between vectors u and v can be represented as beta minus alpha. Doing the dot product means multiply corresponding entries in the vectors and add them up. U dot v is the length of u times the length of v times cosine alpha cosine beta, plus length of u, length of v, sine alpha, sine beta. Obviously, I can factor the lengths of the two vectors out. But recalling our knowledge of trigonometry, cosine alpha cosine beta plus sine alpha sine beta is the cosine of the difference between alpha and beta. Beta minus alpha, though, is the angle between vectors u and v, so this tells me some geometry. This u dot v, which is easy to calculate, is actually the length of the first vector times the length of the second one times the cosine of the angle between the two vectors. We'll always choose the representation for angle theta to lie between 0 and 180 degrees. 0 in pi radians, that is. The reason we prefer that is the inverse cosine can produce angles in that range. Therefore, it'll be all right to rearrange this equation, use the inverse cosine to figure out what the theta is. Theta will be the inverse cosine of u dot v divided by the product of the magnitudes of the two vectors. The problem of calculating angles between vectors is now easy. This argument has been done in 2 dimensions just because the picture is easier to draw, but similar arguments can be made in 3 dimensions, and the conclusion is the same. As an example, let's let vector u be 1, 0, negative 1 component-wise, and v 2, 1, 3. These are 2 arrows in 3-dimensional space with common starting point at the origin and ending x, y, and z coordinates given by the components. I'd like to find the angle between those 2 vectors. They have a common starting point. Each has an ending point, so that's 3 points, any 3 points can be laid down in a plane, the angle that I'm talking about is the angle between the 2 arrows as measured in that plane. The quantities that we'll need in order to calculate the angle are the length of vector u and the length of vector v, both of which we know how to calculate. And we also need to know this new thing, this dot product of u and v. This is straightforward to calculate. Which, according to my calculator, is about 100.893 degrees. Assuming that neither u nor v are the zero vector, u dot v equals length of u, length of v cosine theta tells me something else too. Lengths are not negative. Lengths of non-zero vectors are positive. So this says that u dot v is a positive number times cosine theta. This means that if u dot v is positive, cosine theta is positive, and if negative, cosine theta will be negative. Since we're taking theta to be between 0 and 180 degrees, if I just know the dot product of the 2 vectors, I can tell you something about the angle between them. If u dot v is positive, the angle between u and v has a positive cosine. It is an acute angle. U dot v being negative means cosine theta is negative, meaning I have an obtuse angle. And if u dot v comes up exactly 0, that means that cosine of theta is 0. The only angle between 0 and 180 degrees that will do that is a 90-degree angle, or pi over 2 radians. If u dot v is 0, with u and v being non-zero vectors, then those vectors are at right angles to each other, also called orthogonal, but we'll talk more about that later. Given a triangle in 3-dimensional space with the 3 indicated points as its corners, I'd like to figure out whether I have an acute triangle, an obtuse triangle, or maybe I'll have a right triangle. I want to see about that too. I don't want to do a lot of work though. Form the component form of the vectors from P to Q and from P to R. This will be an angle, if I want to think about it in terms of geometry, that has P at the vertex. It'll be angle alpha. If I form the dot product of those 2 vectors, I get a negative number. This tells me that angle alpha is obtuse, which means both of the other angles must be acute. This costs me very little effort to figure out. To find out about angle beta, I have to know the vector that starts at Q and goes to R, which I don't know, but I can easily find out by using n to minus star. I also need to know the vector from Q to P, which is the negative of the vector from P to Q, and we do already know that one. Calculating the indicated dot product, it comes up positive, which tells me that beta is an acute angle, as we knew it was going to be. To find out about angle gamma, I need to know the vector from R to P, and also the vector from R to Q. On the other hand, we already know the vector from P to R, so this one will be the negative of that. We already know the vector from Q to R, the vector from R to Q will be the negative of that. The dot product comes up positive, which tells me that angle gamma is acute, as again we knew it was going to be. This dot product is obviously going to be important to us in a variety of applications. It has some algebra properties that bear a great similarity to those of ordinary real numbers. I at least want to mention those. In ordinary algebra, if I have two numbers, a and b, then a times b is always b times a. That's the commutative law of multiplication. Is the same true for the dot product? U dot v would be this expression, while v dot u would be this one. All of the things that are in either one of those two formulas are just ordinary numbers now. u1 v1 is the same number as v1 u1. u2 v2 is the same as v2 u2. And likewise, u3 v3 is the same thing as v3 u3. u dot v and v dot u are in fact always the same thing. In ordinary arithmetic, if I have a number a and I multiply it by itself, I get a number that's either positive or zero, and the only way I can get the zero is if the a was zero. What about this dot product? U dot u will be u1 squared plus u2 squared plus u3 squared. None of those numbers can be negative. When you add three numbers together, none of which are negative, the result can't be negative either. So u dot u is at least zero. Also, the only way that you could make u dot u equal to zero would be if u1, u2, and u3 were all zero, meaning that u would be the zero vector. U dot u acts in a way that's very similar to a squared from ordinary algebra. In ordinary algebra and arithmetic, we have what's called the distributive law. A multiplied by the number b plus c is the number ab plus the number ac. In this new setting, working with vectors, is this still true? I want to look at these two expressions and see that if I can't convince myself that they're the same, or maybe, depending on how the details go, maybe I'll see that they're not the same. We'll only know for sure after we try it out. Let's calculate both of these quantities and see what they are. Working out the quantity on the left is straightforward, and now we'll do the one on the right. If you look at what happened on the left versus what happened on the right, that term appears in both places. u2v2 u2v2 appears in both places. u3v3 appears in both places. u1w1 appears in both places. u2w2 and lastly, u3w3. This expression and that expression are the same. U dot v plus w is always the same thing as the number u dot v plus the number u dot w. If I take a number and multiply it by a dot product of two vectors, I get the same answer as if I had multiplied one of the vectors by the number and then did the dot product, or took the first vector and multiplied the second vector by the constant and then did the dot product. The way that you see this is correct is similar to what we were just looking at. This has been a short introduction to the idea of a dot product. In the next discussion, we'll look at some uses of this. I hope everyone's having a good day. I'll talk to you again soon.